Very good afternoon to all of you. We will start the session after 5 minutes.
Good evening, everyone. Thanks for being here today. First of all, I would like to thank to all of you for registering for the fourth session of Faculty Interaction Webinar series on emerging technology for carbon nanotubes, field effect transistors, engineering, innovation, and insights using Synopsys QuantumATK software. So let me introduce today's speaker. It is my pleasure to introduce our esteemed speaker, Dr. Rudra Sankar Dhar, for today's session of the Faculty Interaction webinar series on nanomaterials and device modeling with Synopsys QuantumATK software. Dr. Dhar is currently an associate professor and the dean academics in the Department of Electronics and Communication Engineering at the NIT Mizoram. He has made significant contributions to the field of nano and microelectronics, semiconductor electronics, nanomaterials, optoelectronics, nanophotonics, bioelectronic sensors, solar cells, perovskite materials, device fabrications and characterizations, TCAT simulations, quantum transport simulations, organic electronics, molecular devices, computational and nanoelectronics, VLSI, energy devices, and green nanotechnology. His expertise lies in the advancing materials and device applications through cutting edge research. With the strong foundation in the theoretical and computational physics, Dr. Dhar has focused extensively on the electrical, thermal, and transport properties of carbon nanotubes, as well as the modeling and simulation of field effect transistor devices. Today, he will share his insights and research expertise on utilizing Synopsys QuantumATK software for CNT FET engineering. His talk will focus on how atomic scale modeling and simulation techniques can drive innovations in this domain. After the presentation, we will have an live demonstration on the same topic by Mr. Deepak Upadhyay. He is an application engineer at Integrated Microsystems, a company based in Gurugram, Haryana. He will provide a hands-on walkthrough of Synopsys QuantumATK software for CNT FET simulations, helping you to understand its practical applications. With this brief introduction, I am delighted to hand over the session to our esteemed speaker, Dr. Rudra Sankar Dhar. Sir, over to you.
Thanks. Good afternoon. Am I audible?
Yes, sir.
Yes, sir, you are audible.
Okay. Thank you. So thank you for the introduction. So today I will be giving a brief idea about how we are using CNT, using QuantumATK as the software. So let me open the presentation first. Is my slide visible?
Yes, sir, it is visible.
Okay, good. So, as the topic is for today, so we will be discussing about the carbon nanotubes and its utilization as a FET uh, using the QuantumATK as the software. So this is a very new software which we have been using for some time now, and so we are using it, and it's quite good and it's quite efficient enough where we are able to see
Excuse me,
and
sir. Kindly share your PPT screen.
The slide is not visible, sir.
Yes, sir.
it's not visible. Can you see my screen now? Slides?
Slides are not there.
Sorry,
It's moving actually. Maybe you try sharing the full screen and then change to the place where your PPT is there. Right now we are able to see your Google Meet portion actually with a black window where the presentation is there.
But I don't know, showing it's moving also.
Yeah.
Sir, please try to share the entire screen.
Huh, that is what I'm doing. I don't know what's going on.
Already you have actually shared the entire screen.
Yeah, yeah.
Yeah, now it is there. Now it has come.
Okay, okay.
Can you please put it in full screen?
Yeah, 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 yeah.
Yeah, perfect.
Maybe some internet issues or something, maybe. Yeah. Okay. Yeah. So we'll be over here discussing about how we are using the Quantum ATK as a software for modeling this carbon nanotube FETs. And so, therefore, we'll be seeing about the emerging technologies, the molecular dynamics, and the that are being utilized by the software to um, design the device. So the outline of my presentation will be following some overview, impact of the chiralities on the device performances, NEGF-based device analysis, atomistic modeling of CNT FETs, and the impact of doping on device performance. So quantum ATK basically addresses few key materials and modeling areas, focusing on semiconductors, batteries, solar cells, catalysts, polymers, metals, and ceramics. So we have been using this software for very recently, maybe around a year or so, and we are mostly focusing over here in NIT Mizoram on semiconductors and um, polymers, using polymers and this type of batteries also. So these are the main lookouts in the softwares that we are using to focus in device simulations and different aspects that can be utilized. So coming into the CNT, carbon nanotube, as we all know, is a cylindrically nanostructured composed graphene sheet, which is rolled in two forms, basically single walled carbon nanotubes and multi-walled with number of layers within the system. So this basically exhibits and has very good electrical, mechanical, and thermal properties, and can be obviously used as a cylindrical FET kind of system that we have that can be utilized, and that is the reason why we looked into it to develop our CNT FET. So special feature of this molecular structure is that it is expected to have good ballistic transport because it is a nano wire dimensions, and scalability is quite good. So we can scale down the material based device to a shorter gate length. Um, it is obviously giving a high electron mobility. It has faster switching speed, low power consumption, and good thermal conductivity as such. So basically, considering the device properties and so on, we can say that CNT is a good material for to be utilized as a field effect transistor, and therefore people have also previously or rather recently are looking into CNT as an option um, for alternate silicon materials and things like that. So we figure out this as an alternative option, and therefore we were thinking to design the FET using this quantum ATK as the software, because in quantum ATK the good part of it is that will be able to do some molecular dynamics and see the how the featuring is happening. So coming into the material as a device, so this has also been can be used as a sensor. So CNTs have defects that at the side walls and the end caps to allow the gas molecules or different types of molecular options to be absorbed. So adsorption is possible with CNTs. On the it is having a resistance, so the resistance of CNTs changes when gas molecules absorbs on the surface, because the molecules will be absorbing on the surface, so the resistance of the material as a whole changes, and therefore the chemical groups of different molecules, like say for example some biomolecules for example, or something like DNA, cellulose, and those type of molecules, those can also be utilized, or those can also be added on the CNTs. So therefore it can it is there is a high probability that the CNT can work good as a good sensor, I mean like a biosensor, bio CNT FET or something like that. So that will help in thus the CNT is basically a multiple absorbing site material. It is basically chemically inert. It is biocompatible obviously, because we can biomolecules can also be adsorbed by the thing. Um, also the CNTs are low tox has low biologically toxicity. It is having a high flexibility, because it can be bent and uh, turned either ways to a great extent, rather than in comparison to silicon, which is a hard type of crystal type of material. So therefore CNT will be having is expected to have a better flexibility, and therefore we were looking into this as a material for our new FET, or maybe some other type of devices which we can develop later on. So to more going into the insights of the CNT, we also looked for the chiralities. So this is what we can see over here, the zigzag type of formation of this molecular structure. As you can see clearly, it gives a zigzag molecular structure with N0, and the theta is at 0 degree. So n is the multiple of 3 in this case, and in this case the CNT is metallic. Otherwise the CNT will be a semiconducting material. So we can choose the option based on the type of molecular arrangement in the CNT, and this molecular arrangement again can be optimized using our this software. So we have the option to choose what type of molecules we are using, and how what type of arrangement of the molecule we are actually wanting, because it is a molecular dynamics based software, so we can choose it accordingly, and therefore we can acquire which type of CNT we want to use for our device. Another option is the armchair option. So all armchair CNTs are generally metallic in nature. So meaning they have no band gap, or it is basically a point contact band gap structure. So both the conduction band and valence band in this case, as you can see in this the figure 5, you can clearly see that it is a armchair kind of thing. So the bandings of are in touch with each other, the conduction band and valence band. So therefore this has a metallic behavior, which is due to overlap of the conduction and the valence band, which arises in a different kind of atomic arrangement. And in this also you can see this is a kind of a twisted type of thing. So the theta in this case is 30 degree, whereas in figure 4 it is a 0 degree. So it is a simple tube kind of thing. So that is a better option for the semi as a semiconducting material. So based on the type of chiralities, we can figure out which type how the CNT will work, whether it is a semiconducting or metallic or something like that. So that options we can easily select. So this is the picture of a band structure. As you can see, in this case we have chosen the N0 option for 19.0. So that with the 19.0 option, this is the band structure and this is the diameter of the CNT that we get, which is 14.9 angstrom. So that is the total diameter of the tube with the 19.0. If more we increase the N0, the diameter will actually increase, and diameter of the tube will increase. Whereas if we decrease it, like say for example 13.0, then the diameter again will decrease. So again, this also we can choose easily and select it based on our requirement and the type of option that we are looking for in our device. So the energy gap will be varying accordingly, and therefore you can we can get the um, CNT based on the diameter of the device. So this is the corresponding structures that you can that can develop. So with 19.0 we are having the widest um, option, um, f- where we are seeing the uh, variation of band gap with respect to photosensitivity and the substratial swing for different CNTs. I mean, for different N0 combination of the CNTs. So, so the highest 19.0 is something like this, followed by 16.0. 13.0 is quite small, and then we are having the 10.0 over here, where in 10.0 the photosensitivity is quite high, whereas the substratial swing is quite low. So now it depends on what type of option we are looking into it. If we are looking for more as a photosensitive, to make the CNT work as a more photosensitive material, so we have to choose accordingly. And if we are looking for a lower subthreshold material kind of CNT, so accordingly we can choose. And these are all for the zigzag CNTs, that is the curvature options. So we can choose accordingly. But as we were looking into the CNT FET, so we were looking for we considered CNT as 19.0, so that we can have a lesser photosensitive material, whereas we can go for a medium kind of subthreshold swing. So on that particular, considering that particular scale, we considered the material, and thereafter we went ahead to see how it is varying. So and also, as I said, the diameter size changes based on the chiralities. So that is what we can see from this graph also. So this is what we are getting, the threshold voltage change with increase in diameter of our tube. So if the diameter is increasing, the threshold voltage is also decreasing to a quite extent, exponential decrease, as we can see. So so we should have the um, diameter accordingly. I mean, we cannot go for a very small option, and because the threshold voltage of the device needs to be optimized for a FET. So we went for a 19.0, which is giving a threshold voltage something around zero point 0.3 around. Okay. So next. So next we design the CNT FET. As you can see over here, this is a planar CNT FET that has been designed. So in the planar CNT FET, this is the channel region where the source and drain on the either side. So this is the on the left side is your source and the right side is the drain. So this is a very energy efficient digital circuit, due to which can enhance high electron mobilities, good enough for analog and RF applications where low parasitic capacitance and high frequency options can be observed. So this is a design device through our software, through the software that we have designed. This is a planar CNT, and this is a GAA, gate all around CNT. So as you can see, this is the gate all around structure. The GA design, as we know, offers a higher on and off current ratio and reduced leakage current compared to planar. So we went for a GA option, gate all around device. So initially we developed the channel based on the CNT we want to take. In this case, we chose 19.0 option of chirality, and therefore we took the device, took the channel region, the tube CNT, and therefore we demarcated the source and drain electrodes based on the lengths that we wanted, and thereafter did the oxide and the uh, metals on top of the quantum CNT. This is expected to improve the scalability, making the suitable for ultra small device dimensions and suitable for or nanoelectronics observations. Okay. So as I said, 19.0 CNT, that means our diameter of the tube is basically 14.9 angstrom. Okay. So difference between the CNT, the normal CNT and the silicon MOSFET. So as you can see, this is the basic difference. The structurally, it looks quite similar. Instead of the channel, silicon channel, which is formed, we are having the CNT FET in this case. And it as we are applying the gate along with it, and therefore the energy band diagram at normal condition is given. So in CNT FET, we are actually having a Schottky barrier contact. So currently current is controlled by modulating the Schottky barrier at the metal CNT junction. MOSFET like CNT FET can also be developed if we are doping the CNT regions to reduce the Schottky barriers, and that can easily be done. So CNT FET can also be doped to reduce the barrier, and therefore it can also perform like a MOSFET type of device. Uh, that is what we see over here. In case of a MOSFET, we are actually applying the bias to make the device N channel or P channel, whatever it is. So in this case, the N channel with N channel MOSFET, so that means basically we are depleting the channel region, and this can be done if we are doping the CNT with a similar type of material combination, so that the doping it will act as a MOSFET. Also, the CNT can work as a tunnel FET by using quantum tunneling and ultra low power for ultra low power applications. That can also be possible by doing the tunneling option. So we can basically use CNT FET as a MOSFET also. So that also is a beneficial part of our working with this CNT. So the electron density formation is given something like this. So this is the as you can see from the picture, the geometry. So we have the central region, which is covering both the extension of the two electrodes from both the um, left and right electrode. That means basically the source and drain electrodes are extended, and also we have the channel region in between, which is the extensions, and finally the extended left and right electrode are your source and drain electrodes of the GA device. And this central region covers the extension of the source and drains, and also the channel region at the central part. So the channel region is the full thing is the CNT, and that is giving as the spectral density matrix, and a non-equilibrium electron distribution is generated when we are applying it through our software, and therefore the molecular structure is we can see over here. The output behavior of the CNT at 19.0 for the 30 nanometer gate length is somewhat like this. That is, variations are shown for the different CNTs, IDVG characteristics. So as you can see in the figure 14a, the difference of the IDVGs are shown, 10.0, 13.0, 19.0, 25.0, and so on. So as we are increasing the diameter, we are basically seeing a rise in the on current and also a rise in the off current. So for 25.0, the off current is quite high. So that is why we did not consider, we went for the 19.0 option, which is having a moderate off current and good enough on current. And this is the IDVD characteristics. So so that is what we see in the IDVD characteristics about the output characteristics for a 30 nanometer gate length GAA CNT FET. So the chirality again is we are considering the 19.0 option, which I guess is a better option and giving a better results in corresponding to the other alternatives. So this is the simulation basically we have done. So as I am saying that this is the so this is the first figure A is basically the central region covering the molecular structure of the CNT, giving the device geometrical approach and sensing application. So this is the part of the left electrode and this is the right electrode thing, which is basically your source and drain. And then we have the channel region, which is uh, uh, in this case, this is a 3 nanometer channel length has been considered in this. And a doping material of NH3 ammonia has been used for gas sensing applications. This is the simulated device is shown over here, where we have the channel region where the doping is zoomed in figure B. Um, and we have the extensions shown with the vertical lines for the extension electrodes and the final source and drains on the either side. So this is how the device is observed to be there. This is the analysis of the IDVD characteristics. The normal GA CNT FET, then GA CNT FET with ammonia doped and with nitrogen dioxide doped. So these are the three IDVD characteristics that we can see over here. Target molecules showing adsorption effect in CNT is significant. Minute change in current components for the target molecules are observed. Target molecules are extracted by the CID numbers. So target molecules means basically the ammonia or the nitrogen dioxide, whatever has been used in either of the cases. So that has been done to figure this thing out. So this is how the actual the look of our CNT is looking. So this is the channel region where we are doping with this additional molecule over here. Then this is the left electrode and the right electrode. Scattering event is clearly observed to happen. So this is the region of scattering because that is the reason where the carrier transport is taking place, and the CNT channel remains at conducting stage up to 0.8 volts of the bias range with peak current of in nanoamperes though, but yeah, around uh, in microampere currents we are getting basically. And this is the IDVG characteristics that we see over here. So pristine CNT, CNT with glutamine, and CNT with tryptophan. So these are the three CNTs, CNT FETs that has been designed and plotted over here. So the molecules attached with the CNT remains conducting throughout the bias at 0 to 2 volts with peak current varying from 110 to 116 in either of the two cases. So this is how the sense thing is going on. Amino acids is passing on to the sense as the sensitive element on the CNT, and thereafter it gives the electrical signals. The results show changes in the current and the conductance due to alteration in the geometry and aromaticity for the single walled carbon nanotubes. We have not tried the multi-walled as of now, but we are working still on the single wall CNTs. So the results also shows suppressed density of states leading to increase in electron density, which is actually required to have a higher on current, and so as to have a better on-off ratio for the device to increase the sensitivity of the particular device. So that is required, and we are getting it to some extent on this. So we are able to match the things quite well as of now. It can be used as a biosensor also. So the target molecules are applied as adsorption effect on the CNT is quite significant. So as you can see, this is the channel region where the cancer cells or the molecule we can target the molecules on it, and therefore it can be established as a biosensor for CNT FET. And this is the IDVG characteristics based on the with the target molecule and before the target molecule binding. So you can clearly see how the shifting in IDVG is expected, and this is what we are getting with the single walled carbon nanotubes. For multi-world, it is expected to be a bit better with more better sensitivity and so on. But still, we need to figure those things out. The objectives as of now had been to optimize the doping to possibly achieve higher on current, optimize the possibility to achieve lower off current, and also improve switching characteristics and ensure compatibility with the targeted applications. So this is the device, as you can see, the GA CNT FET. So this is the carbon nanotube, full carbon nanotube at 190, that is 1.49 nanometer is the diameter, and on top of it we have the oxide layer, that is the and then the metallic tube is surrounding the to form the gate. The divisions at the end points are the source and drain on either sides. The region between the channel and the barrier in between is basically the extension of the source and the drain electrodes on either side. So this is the basic brief structure of our device that we designed, and this is how the dopings we have considered for different devices. We considered developed 4 devices in the similar domain area with different dopings, source drain dopings we changed, and also we incorporated channel doping profiles, and therefore it has been updated. And as you can see from the GA structure over here, the diameter, the tube diameter and the oxides are clearly visible. So so that is how the device has been done. So as you can see, the inner diameter and the is shown in the tube for the device, and this is the full device structure. 22 is the full device structure, showing the GA FET and source drain on either sides. Okay, and okay, so this is the calibration graph for our simulation device and an experimental CNT FET. So we did the calibration. So it is to some extent it is quite matching. I mean, I will not say a very good compatible with the simulations and the experimental, but the variation is quite okay to some extent between the drain current versus the gate voltage. and it's following the similar trend. The small variations between experimental and the simulation results are due to the fabricated device, due to addition of 1 nanometer aluminum oxide based nitrogen, which are used, and the hafnium oxide as the gate dielectric. So therefore, the close match between the results also indicate good confirms validity of the device that we are using here. And the actual doping profile of the fabricated device is also mentioned. Source strain, we are using 10 to the power 19, 10 to the power 15 for this particular calibration. That is what we did. This is the IDVG characteristics. This is the IDVG characteristics that are showing for the 4 devices. Um, it clearly suggests that there is very due to variation of the source drain dropping. This is having good impact significantly. Having higher source drain dropping improves the current conduction in the device, while excessive channel doping may hinder the performances. The optimal balance needs to be identified, and therefore the better option needs to be optimized for a better current output based device. Okay. So this is the threshold voltage variation based on the 4 devices. So what we can see is that 0.45 is the lowest threshold voltage that we are getting for our device A. So higher channel doping leads to a higher threshold voltage due to increased built-in potential. Higher source drain doping tends to be a lower threshold voltage by enhancing carrier injection. We are getting on current. We are getting an on current ion has been observed, but device C is giving a better ion, 14.2 in comparison to A having 10.7. This is the I off for the different devices, which is quite good for device A, while C and D is not working well. So that is what we observed. So therefore C and D is expected to have provide a very high leakage. So that these things are were expected, and that is what we were getting. So as I said, subthreshold for the swing for the C and D is quite high, as we can see, whereas A and B, though high, but it's acceptable with these conditions. So this is the IDVD characteristics for the 4 devices, a comparison which shows that device A is obviously giving a much better uh, output performance in comparison to the others. This is a table showing all the different parameters that we have done, um, and so as you can see, the threshold voltage is quite similar for all the 4 devices, whereas subthreshold leakage is best for A, uh, and that's how the thing is. So the gate all around CNT FET are investigated, and we are still working on these type of devices to probably make a sensor type of device, and that is probably the better option to use CNT FET for future. And considering QuantumATK as a software, obviously it is giving good results, which is expected, and giving selective with selective doping, we can control the CNT as it is supposed to be. We are able to reduce the scattering effects in the material. We are able to do the adsorption on CNTs, like using some molecules and something like that. Mm, for example, for doping, we have used the phosphorus as the material. So these type of things can be done quite easily. The observed is due to gate control, and fringing capacitance effects are also observed. So some of the references, and that's all. Thank you. Any questions, please?
Thank you,
Hello.
sir. Thank you for the wonderful presentation. Yeah, participant, if you have any query, they can directly ask with sir.
Hello. Yes, sir.
Yeah,
Am
yeah.
I-
Yes,
Yes,
please.
thank you for this wonderful presentations. Sir, I have a query that if I want to learn QuantumATK software from basics, is there any platform to learn that? Or I have gone through some paid channels, paid YouTube videos, but it is not like that. They have elaborated in detail for from a new learner.
See, for learning quantum ATK, you need to have the software with you and you have to use it. I mean, it's not a very difficult software, it's quite easy and user friendly, I will rather say. Uh, so, yeah, but you have to give some time to understand how to use it. I think Mr. Deepak will be giving a demonstration about the software to some extent now also after this, and you can check it, but you need to have the software. That is the main requirement. Otherwise, though, it becomes difficult to use. Uh,
Yeah, we also have the manual tutorial for the beginner. So that can also help for the beginner to start the quantum software. And also after this presentation, I will give the live demonstration on this tool so that the participant can also have an idea about the graphical user interface and how we can use any kind of simulation.
Okay, sir. Thank you.
And if you have any further queries about working on the devices or something like that, maybe if you're interested for doing PhD or something like that, then my email ID and my details are already given over here on the screen. You can see. You can email me for further research and work using quantum ATK and other um, in this related domains, because I'm working in quite a few domains, as I said, and I'm using this software, and there are other softwares also, obviously, but these are the domains that I'm working on: semiconductors, batteries, solar cells, polymers. Polymers means molecular electronics, basically. Mm, So these are the areas that I'm working on, and uh, if you're interested, we can further work. You can contact me.
Excuse me.
Yes.
Yeah, I have a couple of questions. What are the typical sensitivity of these devices when you have these sensitivity and selectivity for the gas sensing in comparison to the commercially available ones?
It is the sensitivity is quite good enough. So we are able to we are able to do the gas sensing, and also and also biosensor devices. So we are, as of now, we are working on developing biosensors for mostly in the for the cancer cell detection and so on. So the sensitivity is quite at par with what we are getting outside. I mean, that's why I showed that experimental, I mean, the calibration curve. So it is quite good, in fact.
Yeah, yeah, I have a question. And now this threshold voltage is close to 0.4, no? When we compare in this VGS.
For this particular device, it is like that. But yeah, it depends on the device again. Yeah.
And typically, so should one, will we be able to observe sensitivity in this case? Because now the experimental and simulation results are matching only up to zero point 0.4, which is something like a knee voltage, right? And beyond that only we may be able to see some.
Yes, see, for using CNT, that is the part of the CNT, I will say,
Mm,
because CNT is a material where it operates at a very small range.
mm, mm,
Uh, so obviously, I mean, we have to consider something at that range only. I mean, say, for example, zero point 0.4 to 1 volt or something like that, because
mm,
it operates at a very small range. So, I mean, that's the material properties. I mean, maybe if we use a different chirality, we can see at a different range.
mm, mm, mm.
So,
And
yeah,
I also see that in the four cases which have come down further in the slide,
yeah,
number 30 or 29,
yeah,
and I think the case A, as you mentioned, shows very good result.
yeah.
And probably if you tune your parameters a bit, I feel like you are seeing some sort of a resonant-like phenomena, resonant tunneling-like phenomena.
Yes, I am also expecting something like that. That is a thing that we will be obviously looking into it.
Yeah.
So those are the things that, yeah,
Because that is very evident from the
from
IT
the
graph,
graph actually. Yeah,
around that zero point 0.2, zero point 0.3 in that
yeah.
region. If you zoom a little, I mean, if you sample your NEGF calculation a little bit more,
Correct,
and
correct.
in the tight bending approximation, if we, the transport property, which we look at little closer,
Yeah,
and I think it clearly it's as you mentioned, it's distinct from all other cases. BCD is distinctively different, and
distinctively different. Exactly, exactly. We have noticed this, but yeah, we are looking into these findings.
yeah.
So yeah,
Yeah,
but
and one more thing is in these simulations, no, because now the Synopsys is with TCAT for people. I mean, because they
yeah,
have now both DFT results, which are straightforwardly we can connect it to microelectronics.
yeah.
I think as DFT people, we may be in a position to only give a qualitative answer in terms of matching with the experiments. No, and that is very well matching in your case actually.
Exactly, exactly.
The quantitative thing is playing around with the pseudo potentials and hybrid functionals. Then eventually our results will match with the experimental results.
Correct, correct, very correct, very correct.
Yeah, it's good. It's very good work. I am interested actually in looking at the optoelectronics aspects of these CNTs
Mm.
essentially.
Yeah, actually, if we work with this software, so this will be a really good. Say, for example, if we look for developing a solar cell or a laser, also quantum laser or something like that, so
Mhm.
it will be a good option for using this material, because CNT is a very new material. I mean, very less people have worked so far. So we are also cultivating the options, what can be done and what are the further options that we can go into it.
Yeah.
So yeah,
It was a good. It was a good talk and good
thanks.
background. I could see from an engineering perspective how do you look at things, because that is very important as physicists for us.
Exactly, exactly, exactly.
Thank you. Thank you.
Thank you.
It's a nice presentation, sir. I would like to, could you please go through the device structure slide?
Yeah, yeah, yeah.
Exactly not this one. Another one uh, that is another one in the slide I have seen. Right. Previous slide. Please go through the previous slide. Right, this one. Sir, may I know how to prepare this kind of device structure? It's a gate, silicon oxide, and there are some other channels are there. Could you give some outline on how to
Your
make this
channel
kind
is
of?
basically your CNT in this case. Oxide, you apply the oxide, whatever oxide, and whole thing is, in this case, it was made on a silicon device. I mean, silicon material.
Yes, sir.
So on the silicon wafer, we choose the silicon wafer. On top, we are applying the oxide to make the buried oxide kind of thing, and thereafter we are applying, putting the CNT as we place it.
Yeah. Thank you. Thank you for the
Yeah,
information.
yeah. Thanks.
If anyone has any query, they can ask with this, sir, or we will move to the demonstration part. So I think there is no query. So
Yeah, then maybe we can stop. So if you have any further queries or if you want to collaborate to do some related work or something, please email. My email is displayed on the screen, so you can contact. If you want to come for a PhD or something also, that those positions are also there, so please email. Otherwise, okay, thank you.
yeah, so thank you so much. So let me start the demonstration part.
Yes, please continue.
So I hope my screen visible to all of you.
Yes, yes.
So this is the graphical user interface of this Synopsys QuantumATK software that is called Virtual Nano Lab. So let me give some brief idea about this graphical user interface. So you can see this is the project session. So here we have the option to create the new project, and if you want to work on your existing project, then you need to double click and go to the data section. So in the data you can see we have simulated multiple projects. So these are the projects that I have already simulated, and here you can see we have the data filter. Now if you want to filter out everything, so like the simulated structure and also the created structures, then you can go with the everything. If you want to show only data, simulated data, you can see these are the simulated data. And now if you want to show only bulk configuration, you can see these are the bulk configuration that I have created earlier. You can also add your own filter by selecting this add option. So this is the builder that is basically help you to create a desired structure, and this area is called stats. So whatever this structure you will create, that will store here. And this is the 3D view. And here you can see we have the advanced panel toolbar. So in the advanced panel toolbar, you can see we have the various building tools that will help you basically to create a desired structure. Like you can create the FM cantilever TP structure, you can design the amorphous materials, you can also create the alloy structure, you can also go with the nanoparticle, nanowires, even the interface you can also create by using the advanced panel toolbar. So here you can see we have the workflow settings. So this workflow setting basically help you to set up the structure and also the calculation. Here you can see we deal with the various calculation like the DFT LCO method. DFT, this is the device LCO calculator, and this is the plane wave calculator. And we also have the semi-empirical calculator. This is the device semi-empirical calculator. We also deal with the force field calculator, and it also comes with the ground state that will combine with the many body perturbation theory. And here you can see we have the list of analysis part that will help you to simulate either electrical properties, electronics, mechanical, thermal, optical. So all these things you can study by using this QuantumATK. This is the job submission settings. So once you create your workflow, you can go to the job submission settings, and in the job submission setting you can see we have the option to fire the job. You can also fire the job from this GUI to the local machine. You can also fire the job from GUI to the remote machine. So in the remote machine you can see we have the PBS, LSF, PBS Flow, SG, and the server machine. So this is the machine settings. Here you can see this is the editor. So if you are exporting that in the Python script, then you can write your own script here. And if you are not aware, then you can go with the builder and the workflow settings. So this is the viewer. We can visualize the 3D view here, and this is the online database. So in the QuantumATK, basically we have the two options to import the material. Either you can go with the local database that exists inside the software, and if the material is not available in the local database, then you can go with the online database. So let me show the local database first. So this is the local database. Here you can see we have the list of molecule structure. You can also search your molecule here. And this is the benzene molecule. If you want to know more about this benzene molecule, you can see this is the chemical formula. This is the properties like their boiling point, melting point, molecular weight, and also you can visit this link for the more information. So these are the list of molecular structure, and we also have the crystal materials. So you can see these are the crystal, different kind of crystal with the different lattice group like the face center, body center, hexagonal, simple cubic, orthorhombohedral. So all these things we have, and also you can see these are the fluorines materials, and it also comes with the zeolite materials. Like you can see these are the zeolite material, and it also comes with the monomers for the polymer simulation, and it also comes with the ground state element. So basically this is the local database, and here if you want to import some of the material in your builder, you can search the material first. Like you can see this is the silicon alpha. Here you can see this is the chemical formula, this is the lattice information, this is the phase center cubic structure, and here you can see this is the symmetry information. And here we have the atoms and the Cartesian coordinate point. If you want to import this material, you need to click on this add option. Now you can see the material has been added in the stats, and this is the 3D view. So this way we can import the material from the local database, and if the material is not available, then you can go with the online database. So in the online database, you can see we have the crystallography open source database. We also have the material project, and here you can see we have the periodic table. So whatever the material you want to import, first you need to select their element. Like you can see, I would like to select this hydrogen and this oxygen. You can see two element has been selected. Now we need to click on this search option. Then it will search the every possible combination of hydrogen and the oxygen from this crystallography open source database. Here you can see it is searching from the database, and it has searched total 39 structure with the different crystal type. Like you can see this is the simple tetragonal structure, and this is the hydrogen peroxide. So as per your need, you can choose the material. If you want to import the H2O or some other material, you need to click on this arrow and go to the builder. Now you can see the material has been added in the stats. And suppose the material that you want to work is not available either in the local database, either in the online database, then we have the plugin toolbar. So in the plugin toolbar, you can see we have the crystallograph open source database that will help you to import. Basically, we need to enter the COD identifier number. So this is for the crystal, and we have the proximate database. This is for the molecules. You can also go with the link. So this is for the molecule, and here you can see we have the nanotube builder, and here we have the crystal builder. So if you want to work on any new materials, then you can use this crystal builder. First, you need to define the space group. Like you can see, we have the triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, and also the cubic structure, like the face center cubic structure, and also the body center cubic structure. So once you define the space group, then the lattice will automatically selected. We need to define the ABC value, alpha, beta, gamma value. Then we will go with the element and the fractional coordinate point. So let me select a simple cubic structure. Now you can see this is the face center cubic structure, and here you need to enter the experimental value. Like you can see, I would like to take 5.41 angstrom, and you can see this add option has been enabled. So we need to click on this add option, and then we have the various fractional coordinate point. So I would like to go with the XYZ, and here you can see this is the default hydrogen element. If you want to change this hydrogen, we need to double click, and you can see these are the list of element. So I would like to select this gold. Now you can see hydrogen has been replaced by the gold material, and here you can see this is the preview option. Here we have the primitive cell, and we also have the conventional cell. So this is for preview, and this is for building the structure. So here you can add a n number of elements, there is no limitation, and once you're done with the crystal builder, you need to click on this build option. Now you can see the material has been added in this test, and this is the 3D view. So this way we can create any kind of material. So let's focus on the nanotube structure. So here you can see this is the nanotube builder that will help you to create any kind of nanotube. Either it could be a carbon nanotube. You can also create a MOS2 nanotube, SiO2 nanotube. So any kind of nanotube we can create by using this nanotube builder. Here you can see we have the chemical properties. Here we have the carbon at the site A, carbon at the site B. We can also modify the bond distance. Here we have the inner tube, center tube, and the outer tube. So multi-wall nanotube we can design by using the nanotube builder. So if I select this preview, so this is the default option, and here you can see this is the inner tube that has been selected, and here we have the crawl vectors n and m value. You can see n is equal to 6 and m is equal to 0. You can also modify the crawl vector as per your need. If you want to enable the center tube as well, we need to enable, click on this preview. So you can see we have the inner tube and we have the center tube. If you want to add the outer tube as well, you need to enable, select this preview. So you can see inner tube, center tube, and also the outer tube. So this is the multi-wall carbon nanotube. Now if you want to work on a single nanotube, like this is the, I would like to go with the center tube. You can see the center tube has been enabled. Select this preview. And once you're done with this nanotube builder, you need to click on this build option. Now you can see this nanotube has been added in the stats. This is the 3D view. And now you can see this nanotube is quite thin. So if you want to increase the length in any direction, either direction A, direction B, and direction C, then here you can see we have the advanced panel toolbar. So these are the building tools, and here you can see we have the bulk tool. In the bulk tool, you can see we have the repeat option that will basically help you to repeat your structure in any direction, either direction A, direction B, or direction C. So I would like to repeat in the C direction. You can see this is the C direction. I would like to enter the value 10 and select this apply. Now you can see the nanotube has been increased 10 times in the transport direction. And if you want to create an array of the nanotube, then here you can see we have the redo and undo option as well. Now I would like to take 3 times in the A direction, 1 time in the B direction, and 7 times in the C direction. Now you can see, and then click on this apply. Here you can see we have created an array of nanotube. Now if you want to convert this structure into a device, so you can go to the device tool, and here you can see we have the device from the bulk. So this is our bulk configuration. Here you can see if you want to know the information about the any structure, you can click on this I tab, and in the I tab you can see this is the bulk configuration. This is the total atoms, and here you can see this is the lattice type, this is the unit cell, and this is the primitive vector, and also you can see this is the density of the unit cell. Now if you want to convert this structure into a device, you can go to the device from the bulk. So you can see this is the device builder. Here you can see we have the left electrode, right electrode, and this is the center region. So this area is called electrode extension length at the left side and the right side. So this basically help you to reduce the scattering between the electrode and the center region. So if you want to add this electrode extension length, so here you can see we have the option that will help you to add. And if you want to go with the default option, then you need to click on this OK. And if you also want to increase the buffer in the region, in the left region, right region, here you can see we have all the options. Whether you can increase or decrease. So this is the device that I have created for this area of the nanotube. Now if you want to add the gate, like the dielectric substrate region, metallic gate region, source and drain, then you can go to the spatial region. Here you can see this is the spatial region. And before spatial region, if you want to know the like a vacuum space in the direction A, direction B, direction C, so you can select this nanotube bulk configuration. You can go to the lattice information. So this is the lattice parameter. Here you can see this is the this is the vacuum energy in the direction of A, direction B, and direction C.
Hello, 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 hello,
Yeah, hello.
hello, Mr. Deepak. Hello, am I audible? Hello, hello,
Yeah, hello. Yes, sir.
Mr. Deepak. Hello.
Yes, sir. Hello.
Actually, I am having one question. Uh, Actually, you put metal from spatial region, na? So there will be
Yeah, right.
an option for metal and dielectric. So we
Yeah,
can
right.
provide the metal gate from spatial region only. Question is that is there any provision to change the work function of the metal? For example, we want to put gold electrode as a metal. So is there any provision? Because we know that we can put metal electrode from spatial region only and dielectric layer also. So is there any provision? That is my question.
Yeah, sir. That is also available in the QuantumATK. You can also change the source. If you want to add the gold material, then you can also add. And if you want to define their work function,
Source
here you
and
can
drain I
see.
know. Source and drain I know that we can provide by molecular junction
Yes.
that is available from tutorial is available. Source electrode and drain electrode can be modified as gold electrode or any other metal electrode. But the metal gate means, for example, cylindrical gate all around structure. So we need to put a cylindrical metal, na? So that metal can we provide gold electrode for?
So, sir, basically, we need to change their value, then it will become a gold or something, graphene something. So, let me cover this one.
Okay, okay.
So, here you can see.
Okay. For metal value, for example, is in voltage. For example, in negative voltage or positive voltage,
Yeah, that we need to define in
like
the
that, no?
value option.
Okay,
Yeah,
okay.
that we need to define here. So here you can see this is the region type, and we need to click on this add option. And here you can see this is the metallic region. If you define the value for the
Yes, yes,
gold
yes.
material, then it will become a gold metallic. And suppose I would like to take a dielectric region, and if you want to define the
Dielectric,
SiO2,
yes, yes. 30 epsilon naught, for example, 27 epsilon naught. That value
yeah,
can
that
be
we need to
given, and
define.
metal value has
Yeah.
been given. Uh, okay. Only
So
by
let
changing the value of the metal, we can make
yeah
it like.
that yeah it will become a gold or something SiO2 something that you can define. So I am selecting this dielectric substrate region, and here I need to change the value. So for the SiO2, I would like to put a 3.9, and here we need to go to the geometry option. In the geometry, you can see this is the box, we have the sphere, we have the tube. So we have created a nanotube, so we need to select this tube option, and here you can see we need to define the start point for the direction x, y, and z, and the end point for the x, y, and z. And here we can also define the inner radius and their thickness of this dielectric substrate region. So if you want to know the value for this end point and the start point, you can go to the carbon nanotube, the bulk configuration. Here you can select the lattice. Now you can see this is the lattice value in the direction x, y, and z. So this is the spatial region I would like to add in the device. And here we need to change the start point and also the end point. So I would like to go with the spatial region, and my starting point will be 0, and here the ending point will be 44.1005 in the x direction, and also in the y direction. I would like to take 4.
And sorry for in the interruption. And one more thing is that it is like lateral. It is, we know that NEGF formation means lateral CNT. But is there any provision to put vertical CNT by maintaining the same NEGF calculation structure?
So sir, for this vertical CNT, we need to rotate the tube. So we have the option here. You can see if you want to design a vertical. So this is the horizontal. If you want to
Yes.
take a vertical nanotube, you can go to the rotate option. Here you can
Okay.
see this is the rotate cell,
Okay.
rotate atoms, and we need to define the angle and also the rotation axis. So if I take the 90-degree, you can see this is the 90-degree in the direction x I have selected, and then you can select the supply. Now you can see the tube has been rotated 90-degree in the
Right,
x
right.
direction.
Perfect,
Yeah,
perfect.
so
Thank you.
this way we can create. So here, let me cover this one. So this is the tube. If you want to select the box, now let me cover the box. And this is the dielectric substrate region. This is the metallic. This is the dielectric. And we need to define the parameter in the x, y, and z. So for the x, I would like to take 14.1005. And in the y direction, I would like to take 0 to 4. And in the c direction, I would like to take 0 to 29.83. Now you can see. This is the dielectric substrate region that we have added. Now if you want to add the metallic region in this structure, so if you want to add the metallic region, again we need to select the side option. Sorry, here I would like to take 3.9 for the SiO2. Yeah, this is the metallic region, and again we need to define the region. So in the x direction, I would like to take 0 to 44.1005, because this is the vacuum energy in the direction of x. And I would like to take 0 and to 14.7002 in the y direction, and in the z direction I would like to take 0 to 7. Now you can see this is our
Hello.
yeah
Hello.
hello.
One more question, last but not the least, but last almost. So gold nanoparticle can be found from periodic table or something like that. But gold nanoparticle, gold is there, EU is there in periodic table, but gold nanoparticle, which is completely different from gold, actually, conventional gold. So that can be modify the surface of the CNT, bare CNT you have taken. That surface can be modified by the gold nanoparticle or any other metal nanoparticle, because doping is something different or selective doping something different, but the coating is something different, because we can take n type and p type doping from QuantumATK as well, from that one spatial region, that up the upper spatial region, that can be done. But the thing is that we coat no, I am not asking about doping, but can we coat the surface of the CNT? Is there any provision like that?
Yeah, that is possible. So first you need to create your nanoparticle by using the advanced panel toolbar. Here you can see we have the nanoparticle builder. So let me, yeah, this is the nanoparticle. Here you need to import your gold material in the core and cell, and then you need to define the core radius, gap, and the cell thickness. Once your nanoparticle is ready, then you can go to the absorption settings. This one, because I have selected a device, so this will not enable. So once you create a bulk configuration, you can see this absorption has been enabled. So first you can create your nanoparticle, then you can create your nanotube, and then you can go to the absorption settings. And here you can see we have the load from the file. Basically, we need to import our nanoparticle structure. Then it will create over the surface of the nanotube. So I hope your question is clear now. Okay, no, sir. So
Yes,
let me
yes.
cover
Thank
the
you very
device.
much.
Yeah, so let me cover this device. And after this demonstration, we will come to the question and answer. So this is the spatial region that I am going to add in this device structure. Now you can see this is the metallic region, and here you can see I am putting 0 to 44.1005 in the x direction, and the y direction 0 to 14.7002, and in the z direction 0 to 7. And this for the source. If you want to add one more metallic region in the drain side, so let me add one more metallic region. Again, you can define the positions in the x, y, z, and if you want to add one more gate, we need to select this metallic region. So let me add the gate material first. So for the gate, I would like to select their position in the x direction from 0 to 44.1005 in the x direction, and in the y direction I would like to put from 10.5 to 14.7002 in the y direction, and in the z direction I would like to put from 12.8 angstrom to 17. Now you can see this is our gate, and here we have added the source, and here we will add the drain. So in the drain, I would like to define the position for the drain as well from 0 to 44.700, sorry 1005, and in the y direction from 0 to 14.7002. This value I am taking from the vacuum energy that I have already shown how we can calculate that. And here you can see in the z direction I would like to put from 23 angstrom to 29.83. Now you can see this is the source, this is the drain, and this is the metallic gate. So our device is ready, and now we will move to the workflow. So you can see this is the device structure that we have created with the source, drain, and gate. And now we need to define the calculator settings. So in the calculator we have all the options. So you can see this is the device LCO calculator, and this is the device semi-empirical calculator. So if you want to compromise with the accuracy, then you can go with the semi-empirical calculator. If you want to achieve the higher accuracy, then you can go with the device LCO calculator. So let me select the device LCO calculator. And if you want to change any of the parameter in the device calculator, like their spin polarization, their exchange correlation function, so you can see this is the basic parameter that we need to define before the simulation. So if you want to include any kind of spintronics application in your device, like the unpolarized, polarized, non-collinear with the spin orbit coupling, and here you can see we have the exchange correlation function like the LDA, GCA, meta GCA, and the hybrid function, and also we have the custom option that will help you to define your own exchange correlation function. This is the pseudo potential that we have in this QuantumATK, like this single zeta polarized, double zeta polarized, double zeta double polarized, single zeta double polarized. And also you can go with the numerical accuracy. Here you can see we can define the broadening temperature of the whole devices. We can also define the density cutoff energy. And here you can see we can also define the cutoff energy. If I show the device algorithm, here you can see this is the device algorithm, and here we have the green function method. So this is the equilibrium green function method, and we also have the non-equilibrium green function method, and it also comes with the sparse green function method. So it is a user defined, and here you can see this is the electrode part. If you want to define the voltage, temperature at the left electrode, right electrode, then you can also modify that. And here you can see it also comes with the Poisson solver. Like you can see we have the solver type, like this is the direct conjugate gradient, non-uniform grid with the conjugate gradient, and also the multi-grid. Like if I select here, you can see periodic Dirichlet and von Neumann. These are the boundary conditions that we can select. So once you define all the settings in the device LCO calculator, then you can go to the analysis part. And before analysis, if you want to optimize your device configuration, then you can go to the optimize and dynamics. You can also search here. You can see this is the optimized geometry for the material, and we have the optimized device configuration. Like you can see this block has been added, if you want to change any of the parameter, like here you can see, we can also passivate the electrode surface, left and right. We can also define the optimization region length. You can also select the optimization region center. And here you can see, we can also define the force tolerance, maximum number of iteration steps. And also you can define the maximum step size. And this is the optimization method. So this part is for the optimization. And once your optimization done, you can go with the analysis part. And suppose if you want to calculate the like IV characteristics or IDVG some things, then you can go to the IV characteristics block. Now you can see this IV characteristics has been added. If I show you the settings, so these are the basic parameters that we need to define. Here you can see we need to define the gate to source voltage. There are minimum gate to source voltage and also the maximum gate to source voltage, and then you can define the point. Here we have the option to define the drain to source voltage, and here you can see we can define the work function. Here you can choose the electrode, either left side, right side, then you can define the work function as well. So if I select from 0 to 1 and in the point of 10, now you can see this gate to source voltage has been added. And if you want to go with the more analysis part, like the current density, device density of the state, effective potential, electron density, electron difference density, that you can easily add. Now let me calculate the IV characteristics for this device. You can go to the editor to generate the Python script. Now you can see this is the Python script. So in this QuantumATK, there is no need to write any script for any structure. Simply you can create your structure in the builder, go to the workflow settings, and then you can go to the job submission setting, editor. Then it will automatically generate your Python script. And this Python script is also editable. So before simulation, if you want to change any of the parameter, that you can change and go to the job settings. Now you can see this is the local machine that we have added. You can also go with the remote machine that I have already shown you. So in the job tab, you can see we have the serial that will run on a single core and single thread. If you want to define the number of thread, you can go with the threaded parallel. If you want to define the number of thread and number of processor at a time, then you can go with the multi-process parallel. And then you need to select this add option. Now you can see our project has been added and now the state is pending. So if you want to simulate, you need to click on this play button. So once you click on this play button, then it will start the simulation, and here it will generate the log file. So whatever the background simulation is ongoing for this project, that you can show in the log file. So I have already simulated this device structure, so I will show you in the data. And if you want to define the GAFET structure, so if you want to define the GAFET, so here you can see we have the option. So let me select this device. Let me select a nanotube again. This is the nanotube. I would like to take 12.0 and select this build option. Now I would like to click on this repeat option so that we can define their gate source and drain. So I would like to take a single nanotube. Now I would like to take here 12 tons. This is the 2, and then apply. So we have created a nanotube. Now we will convert this structure into a device, and then we will design a GAFET structure gated all around field effect transistor. Now you can see the device is ready. We need to move on the spatial region. This is the spatial region, and here we need to select the dielectric region first. And here I would like to take the SiO2, and for that I would like to put the value 3.9. Here we need to select the tube for the GAFET, and here we need to define the start point and end point for the X, Y, and Z. So here I would like to take 9.70015. So I would like to put from the starting point and ending point in the x and y direction, and in the z direction I would like to put from 8.5 to 34.2. Now you can see this is in the center position. If you want to increase the length here, you can easily define, like if I select the 40, now you can see. So I would like to go with the 43 something. Now here we need to define the inner radius. So I would like to take 5 angstrom. Now you can see. In the similar way, we need to define the metallic region. So let me select a metallic region. So this is the metallic. Again, we need to select the tube. And here again, we need to define the starting point and the ending point for the all the direction, X, Y, and Z. So you can see I am putting all the same similar value. Here basically I need to change from 8.5 to 42.5, and then we need to increase the inner radius. So in the case of dielectric substrate region, I have put it the 5. So in the metallic region, I would like to take 6 angstrom. Now you can see our graphite is ready. And again, you can go with the workflow builder, and you need to define all the parameter and also the IV characteristics parameters. Then you can easily simulate. So let me cover the simulation that I have simulated earlier for the array nanotube, and where I have simulated the IV characteristics and also the projected local density of state. So here you can see this is the device that we have simulated. So similar device I have simulated. Now you can see this is the IV characteristics. So we have taken from 0 to 1 in the point of 10. Here you can see this is the plot type. Here we have the gate to source. You can also go with the drain to source. And here you can see this is the current scaling, linear, logarithmic, symmetric. And also you can go with the electrode temperature if you want to enable. You can click on this enable and then you can simulate. And if you want to calculate their scattering properties, you need to select this graph. You can click on this arrow and select where, yes. Now you can see this scattering simulation has been completed. Now we will go with the device configuration, and here you can see we have the polymer analyzer, molecular dynamic analyzer, and also we have the transmission spectrum analyzer. So this is the transmission spectrum analyzer for this device. Now you can see this is the transmission spectrum with respect to energy, and we also have the transmission spectrum with respect to coefficient. You can easily calculate the spectral current with respect to energy. You can also change the chemical potential and the temperature in the left side and right side. You can see this is the spin value, and this is the spectral current with respect to energy. Here we have the conductance value, specific conductance value, and also the resistance area product. This is the thermoelectric coefficient, like you can see conductance, and that you can easily simulate. Here you can see this is the Seebeck coefficient that we have simulated for this device structure. So this way you can use this QuantumATK software for the device simulation, and also you can use it for the material simulation. And if I show you the help option, you can see this is the help. Here we have the QuantumATK manual. This is the tutorial. We also have the open document and tutorial. You can type QuantumATK. Here you can see this is the QuantumATK documentation. We have the tutorial, we have the manual, and we also have the publication papers. Now I have shown you how you can calculate the nanotube devices structure, like the array of the nanotube and also the GAFET structure. So if anybody has any query regarding this particular session, then they can unmute the mic and ask me the question.
Hi, it is a good presentation. I have a small question. How to twist the geometry?
Yeah, sir, that we can twist. So let me go to the data. This is the builder. So let me take this carbon nanotube, a single carbon nanotube, this one. If you want to twist at any particular angle, you can go to the rotate. Here you can see this is the rotation. Here we need to select the axis and here we need to define the rotation angle so that we can twist this nanotube. And also we have the wrap option. We can also wrap the tube. Here you can see. And this is the wrapping in the switch tube. You can see. So we have all the options.
It
Either
means
twisting, rotating.
it is how long it will be twisted. It means how many nanometer it is twisted. It is sudden twist or it is gradually the twisting is increasing with respect to the length.
So
Could you provide
basically for
some?
rotating or twisting the seat, we need to define the angle. If you want to go with the 90-degree, you can see. It has twisted 90-degree.
Okay, it means it is a sudden. Uh, it is a
It is
sudden
creating
twist.
basically in the Z direction. You can see.
Okay, it means one end to second end there is a 90 degrees. It is twisted overall that length,
Yeah,
right?
yeah, right.
It is not sudden twist at some particular point. It is a twist along that particular axis.
Yeah, right.
Thank you. Thank you.
Okay, sir. Thank you, sir. So if there is no query, then I am going to share my contact details.
I have a general question. Hi Deepak. I have a general question.
Yes, sir. Please tell me.
Yeah, I have a Quantum ATK 2019 version.
Okay.
2019. There, these 2024 options are not available. Could you suggest how to upgrade it?
Okay, sir. No, so after this session, we will have a like a telephonic conversation regarding this.
Thank you.
Deepak, I have a query.
Yes, sir. Tell me.
Say, suppose we have a graphene layer
Okay.
and we do some sort of modification on the on this layer. Now, if I want to find the change in the work function or maybe the work function of this new layer, can that be done?
Yeah, sir. That can also be done. So let me go to the tutorial part. So we have all the tutorial regarding the work function, devices simulation, material simulation. You can see we can tune the work function for any of the devices, any of the materials.
Mm-hmm.
Yeah.
Okay. Thank you.
So I will also share the document and tutorial link. So you can also follow that.
Sure.
So whenever you get the time, you can visit the site. Then I hope you will be more familiar about this tool.
So I think no more queries are there. So as we have come to the conclusion of this insightful session, so it is my honor to extend our deepest gratitude to our esteemed speaker, Dr. Rudra Sankar Dhar, for taking the time to share his insightful on emerging technologies on CNT FET engineering, innovation and insights using Synopsys QuantumATK software. Dr. Dhar, your presentation was truly enlightened and provided us with a comprehensive understanding of modeling and simulation of CNT FET devices at the atomic scale. Your expertise and in the depth explanation of electrical, thermal, and transport properties of carbon nanotubes, along with the quantum ATK's powerful simulation techniques, have been incredibly beneficial to all the attendees. We truly appreciate your effort in making this session engaging and informative. Your knowledge and passion for research in nanoelectronics and advanced materials have undoubtedly inspired many of us today. I would like to take this opportunity also to thank all the participants for their active engagement and thoughtful questions, making this session even more interactive and valuable. Once again, thank you, Dr. Dhar, for your time and sharing your expertise with us today. We look forward for more such enriching sessions like this in future. So thank you all for joining. Have a great evening.
Thank you.
Sir, is there any feedback link, sir?
Yeah, the feedback link we will provide after this session.
Okay, thank you, sir.